Hi, this is Faizy Ahsan. I'll be presenting our project PhyloPGM, which was accepted as submission number 80 in ISMB 2022. In this presentation, I will show you how we can use evolutionary information to, to boost the accuracy of, previously trained sequence-based predictors for transcription factor binding sites and RNA binding protein binding sites. Transcription factors are proteins that bind to specific patterns of 8 to 14 base pair length. And by doing that, they regulate the expression of nearby genes. Computational prediction will allow us to comprehend the gene regulatory networks and associated diseases. A typical computational problem is that you will be given a sequence of 100 base pair length, a transcription factor, and the goal is to predict whether the transcription factor will bind to the sequence or not. Similarly, RNA binding proteins or RBPs bind to specific RNA sequence motifs of 4 to 10 nucleotide length and regulate the post-transcriptional phase of gene expression. Similar to transcription factor binding sites, the computational prediction of RNA binding will allow us to comprehend the post-transcriptional gene regulatory network and the associated diseases. Here also, the problem will be presented as that you'll be given a sequence of 100 nucleotide length, RBP, and the goal is to predict whether the RBP will bind to the sequence or not. Both transcription factor binding prediction and RBP binding predictions suffer from many uh, difficulties. There are many challenges as the binding features depend on many factors. For example, presence or absence of cofactors, epigenetic factors such as histone modification, chromatin accessibility, sequence structure, and so on. And on the top of that, the data itself is highly imbalanced, such that the number of sequences that do not bind to a transcription factor or RBP is huge, due to which the computational models are often prone to high false positive rate. Also, using evolutionary information is challenging due to a phenomena called binding sites turnover, where the sequence properties such as binding sites may be maintained, but the sequence itself may not be conserved. The motivation for our project is that we can augment the training data with the orthologous regions from existing species and ancestors. For example, let's say we have these human sequences. The green represent that they have binding sites and the red represents that they do not. Then we can see that we can find a decision boundary to classify these sequences. Now, if we have more sequences, so that if we add orthologous sequences, then we can see that we can find a better decision boundary. In our study, each human sequence is complemented with around 80 orthologs from ancestors and existing species. So the problem statement for our project is that we will be given a human sequence and its associated orthologs, and also previously trained transcription factor binding site predictor or RBP binding site predictor. And using that predictor, we can obtain scores on the orthologous regions. Now, once we have these prediction scores on the set of orthologous regions, then the goal is to aggregate all those prediction scores such that the accuracy on the human region is improved. In this slide, I show you the workflow of PhyloPGM. So for a given human sequence, We will be having its corresponding orthologous sequences in ancestors and the existing species. The first diagram shows the phylogenetic tree that relates all these orthologous regions. Now, once we have these orthologous regions, we use the base predictor which is trained on, which is a sequence-based model and trained on human sequences only to obtain the prediction scores for all the orthologous regions. Once we have these prediction scores, then we can form a prediction score tree. Now, in our PhyloPGM score computation, we consider the so in this first of all in this prediction score tree, the nodes represents the prediction scores from the base predictor. The weights on the branches, they represents the log likelihood ratio, such that what is the conditional probability of a score of child of a child given its given the score of the parent, and when the human label is 1 and when the human label is 0. So in our computation, we consider human as the root in this prediction score tree because we want to improve the prediction accuracy of human. And we use this these equations to compute the branch log likelihood ratios. In the next slide, I will show you how we can compute these conditional probabilities. Once we have these branch log likelihood ratios, then we aggregate them using a hyperparameter. So this first term is the log likelihood ratio computed for human only, and the rest is for the branch of this prediction score tree. Once we compute the PhyloPGM score, if the PhyloPGM score is above 0, then we term the human sequence as a binding site. Otherwise, we term the human sequence as not binding site. So how do we compute the conditional probabilities? In our computation, what we do is first to round all the prediction scores to their first decimal place, because we want to use a multinomial distribution to compute the conditional probabilities. Once we do that, then let's say we are given a human test sequence, and the corresponding test sequence in chimpanzee had a prediction score of 0.6 and its ancestor had score of 0.7. Then we query in the train set such that the ancestor had the score of 0.7. And so in this table, I show you all the cases where the ancestor had 0.7 score in the train set, and all these values are the values of the chimp sequence, and the Y represents the label of human. So the top row show all the cases where the ancestor had 0.7 score in the train set and the human label was 1. Then we can see that the density of the conditional probability of score of a chimp given the score of its ancestor and the human label as 1 will be high if the test sequence is indeed a binding site. And if it's not a binding site, then the density will be low. So we compute our conditional probabilities using this approach. And once we have those values, we compute the log likelihood ratio to get the branch log likelihood ratio values. And once we have these branch values, then we just sum it up to compute the final PhyloPGM score using a hyperparameter. The role, also one more thing, the role of hyperparameter is to balance the effect of the contribution from the branches to the human prediction score. In this slide, I show you the results with the PhyloPGM approach. So what we did was we applied PhyloPGM to a chipset dataset where we had 13 transcription factors. So I show you the comparison between three models. FactorNet is our base model. FactorNet is a hybrid of a convolutional neural network and recurrent neural network, and we use it as a and it is trained only on human sequences. Phylostack NN is a vanilla neural network which is applied to the prediction scores obtained from FactorNet, and PhyloPGM approach is our approach which is applied to the prediction scores obtained from the FactorNet. We can see that with the PhyloPGM, we had significant amount of improvement over the base model and the vanilla combination. And not only that, we observed a significant amount of improvement in the recall score with PhyloPGM at low false discovery rate. Next, we applied PhyloPGM to RNA binding prediction task. Here we used the ClipSec data where we had 31 RBPs. And here also we can see that PhyloPGM had a significant amount of improvement over the base model. So here the base model is RNA Chapter, which is a hybrid of a convolutional neural network and a recurrent neural network. And PhyloStack-NN, as I described earlier, is a vanilla neural network that combines the prediction scores from RNA Chapter. And PhyloPGM here combines the prediction scores from RNA Chapter. And the RNA Chapter was trained only on human sequences. And we can see that with PhyloPGM, we also had a significant amount of improvement in recall score at low false discovery rate. One thing to note is that the amount of improvement with the RNA binding prediction task is low compared to the transcription factor binding site prediction problem, probably because RNA binding sites are more conserved. Then we wanted to explore like how useful is PhyloPGM in identifying the putative binding sites. So here, what we did, we used the CleanVar dataset. So CleanVar dataset has all those sequences where a mutation is linked to a disease. And then we can see that using PhyloPGM, we were able to identify more putative functional sites compared to the base model and a conservation-based model. So to conclude, PhyloPGM is a probabilistic graphical approach model. It's based on probabilistic graphical techniques that improves the accuracy of a previously trained sequence-based TA transcription factor or RBP binding site predictors. And not only that, PhyloPGM is likely to identify putative functional sites. In future, we would like to handle some more cases, such as for a given human sequence, it could be a case that corresponding orthologous sequence in certain species or ancestor is missing. For now, we handle those cases as a special case, but in future, we would like to have a robust method. And finally, we would like to extend PhyloPGM to regression and multi-classification tasks. Here, in this project, the PhyloPGM is designed for a binary classification task. But in theory, it should be applicable to other kind of machine learning problems as well. And solving those problems will have impact on applications such as prediction of RNA subcellular localization, protein-protein interactions, microRNA target gene prediction, and so on. One thing to note is that to apply PhyloPGM to these kind of problems, we need a base predictor which should be at least better than the random predictor, and also the sequence function should be maintained in the data sets. With this, I would like to thank my co-authors Zishal, Doina, and Matthew, and also my lab members, and also to our funding agencies. Thank you.